Hello everyone, my name is Sato, I'm from Fujitsu. So this is my title toward practical quantum computing and meeting the challenges. So we are really having this goal of making something practical. And so I would like to share with you today our progress so far recently. Now this shows our strategies for quantum computing, which we actually shared with you last year. As you can see here, from drive level to platform to software, we are really focusing on everything, but we're not doing this alone. As you see here, we're working with many researchers outside of the company. And as you know, there are different types of hardwares, and we don't really know what will be the ultimate hardware solution. So we try to make sure that the software technology that doesn't depend on any specific one. And regarding hardware technologies, we would like to work on different things, but because the resource is limited, we're working with Riken on superconducting quantum bit technology, and also we're working with Delft from the Netherlands on the diamond spin. And for us, application is very important. So for many, many years, actually, even before we started to work on quantum computing, we've been working on application development using simulator on the application development. And this shows, well, actually, quantum computing alone, without anything, can be usable and really useful for our users yet. So we are using HPC or digital annealer, which is really fit for optimal for combinatorial problem solving. So that they can be also combined with quantum computing to solve the customer's problems. Now, regarding superconducting, a year and a half ago, we started to work with Professor Nakamura at RIKEN, and we developed this re-released 64-qubit quantum computer a year and a half ago. And actually, this was the second domestic quantum computer in Japan. And 22nd last month, 256 qubit quantum computer was talked about in our press release. And we stopped the refrigerator and opened it, and we show the inside. And so you see here the 256 quantum bit chip. And actually, the chip designed by Professor Nakamura is really scalable. It has the interconnect from the backside. So because of this, it can be expanded. It can be made into a larger scale. But there's a big question mark yet. We started to work on this some years ago, and still there's a major question. At the time, available refrigerator was limited to 64-bit per plus one. So we weren't sure if this chip can fit into this and be able to actually cool it. And also we weren't sure if the 4 times higher density was possible to begin with. And so first, we calculated thermal. We actually conducted a very precise thermal calculation. So we use 4 times of components, and for different layers. I mean, in refrigeration, there's a 4 different, different stages, and we realized that at this 4K stage, there's HEMT, and that consumes a lot of energy, and there was a lot of risk we found out. So we reviewed the HEMT components, and also we looked at the housing design to improve cooling efficiency so that we wouldn't have any problem in the 4K stage. And another point that we really worked hard is this package, because the scope, the space of the refrigerator is limited. So you see here, this is the one 64 Q chip, and the other one is 256. So it's 4 times greater in the surface. And if you have the package size, which is 4 times bigger, it will be too much in terms of the volume. It couldn't be housed. So we changed the connectors, and we made small improvements in different paths. And for example, this bottom plate size had to be enlarged a little bit, but still all the wirings and the chip itself was cased. As a result, And at the same time, so we laid out all the components, and because we had to house the 4 times greater in terms of the components, and it's not only okay if we can put cram everything inside. We have to be able to assemble them. We have to be able to disassemble them for maintenance. So we conducted a very careful design to allow that, and you see the result here. Also, another thing we did is because we've changed from 64 to 256, the number of the chips go up. The Josephson junctions is limited, and the chip air there will be the junctions variation coefficient of variation device resistance will occur, and so. For example, you see the Josephson junction resistance is shown here at the bottom, and there's an inductance put into on this, and then that will have an impact on the frequency. So by having the resistance consistency, we can manage control the frequency. And initially, it was 4.01% right after before the improvement, and we conducted laser annealing, and then we made them into automatics and made it into a real system. Another element was time from 60 to 256, that means 4 times greater. And at the time when we had the 64 bits, we were using the system, and when we were using the same system, it will take 36 hours to control all or just all the chips. And you know the Josephson junctions exposed to air will start to change the properties when exposed to the air. So we had to shorten the adjustment time to 1/3. And so based on this effort, now using laser ink, probably in terms of the frequency, we were reduce this to 0.3%. And so it wasn't very easy, of course. And then because of the consolidation of many different techniques, we were successful in being able to operate with 256 bits. Now, today we're conducting this, and we're still tuning this yet. And at earliest, by the end of June, we'll be able to make it available for the co-researchers. So this was about the superconducting quantum computer, but we are actually delivering other equipment like simulators. And this is something we talked about last year too. We have the staging vector method, 40 quantum bit is the simulation simulator type that we have. And the quantum volume is growing all the time. And 2 to 23 bit used in 23 steps. So now the simulator provides us more calculations. So still for researchers, simulator is a very important tool. And that is why we continue to deliver such simulators. And this is actually used by companies, the customers, to develop applications. But there are customers who want to simulate with more quantum bits. So that is why we are delivering the the tensor network simulator, and also we are developing supercomputing with supercomputer, and also we are providing other simulators working with the Tokyo University. Another thing we forgot to mention is we also do this quantum computer challenge, and last year we did second time, and then there were as many as 50 companies who wanted to participate. So that is part of the way we try to develop applications. So we now have 265 bit, and then we have the simulator, and we have the quantum computer, and we have this hybrid platforms. So customers can choose between the quantum computer or simulator, or in case of quantum computer, they can choose between 64 to 200 or 256. And at this point of time, quantum computing cannot do a very long time calculations. So hybrid algorithm does work like VQ, but beyond that, even one part that is run by quantum computer is split. For high accuracies required portion, we let them use the simulator instead.
I showed you earlier the platform. In the beginning, We are the only one developing this, but currently we are working with Osaka University to develop software. The other day, Osaka University uh, released this platform as OSS along with us. We have to add more components to this platform. So community members are invited so that we can together develop the platform. As I said, using this platform, the companies that are indicated here and we are working together. We are not material manufacturer. It's not that we understand direct problems customers have. By working with customers, we will better understand their real problems and we'll be able to eventually solve their problems. So going forward, for the time being, what we are doing is, as I introduced in my LinkedIn, since last year, the end of last year, 1,000 qubit system will be launched in Fujitsu Technology Park, close to Musashi Nakano on the Nambu line. We have a major office there. And beside that building, we have begun constructing this 1,000 qubit building because of the gigantic size of refrigerator that is necessary. We'll be able to complete this in coming October. There are various designs for qubits, 1,000 qubits. Eventually, we'll be able to disclose what we are doing next year. As Mr. Shimada explained early on, 2 days from today, on Sunday, GQuad is going to make announcement, and we have provided this superconductive computer to GQuad. And not just in Japan, this prototype system that we have, we want to deliver overseas as well. Prototype business is something that we want to promote that is important to our company. And what we want to do is to offer this to overseas customers so that we can eventually work together to develop applications. Another thing, this is a different topic. It's not just semiconductor. Diamond spin quantum technology is something that we are already working on. Defect within diamond, the electron spin in that defect will be utilized for quantum computing. It's not just that electron spin, but nuclear spin. MD Center has nitrogen that has spin, and isotope spin can also be utilized. Less than 10 of them as a group, we call this the nuclear spin. And you can use photons to communicate that. So it's a photonic link that can be utilized to connect. And this can be utilized for scaling. As you know, photonic line is very resistant to noise. It can be connected in room temperature, at room temperature level as well. Another reason why we are working on this is this quantum bit. Doesn't have to be freeze down to very low Kelvin level. So you can minimize the refrigeration size. Although this is still the early stage of development, we believe, but we have been working on this joint research since 2020. It's not just qubit that we want to develop. Cryo CMOS, the control system, should be placed on a chip. And that is also another purpose of this project. This is a recent news. Using this technology within the module, electron spin and 2-qubit gate can be introduced. By doing so, we'll be able to achieve fidelity over 99.9%. To be precise, there will be 99.92 or 93. This is gate set tomography using HPC resources. We get this result, so I think the accuracy is pretty high. For one bit, it is over 99.99%. It's not just a superconductive quantum. We would like to utilize this nuclear spin, to develop quantum computing. And we actually had this press release in March. As I said, we are working on software as well. This is one example. Keysight, we had the Professor Joseph Emerson working with us in the joint project, and that developed into Keysight collaboration for error mitigation. This is one example. Randomized compiling is explained here to eliminate coherent error. In this case, ion trap devices indicated here. We can apply that to see error is suppressed. As you can see, errors can be controlled and suppressed substantially. This is just one example that we are working with Keysight. Another example. This is a heavy topic. Error correction is something that we are focusing on, as you know. We still have the 100 qubit NISQ error is something that we are working on. And I believe we have to have eventually 1 million qubits because we need resources for error correction. Error correction, after that, logical gate operation is something that requires more resources, especially non-Clifford gate. And the question here is how we can reduce the resources that are required. Unless you achieve error correction, even though you have 1,000 qubit or 10,000 qubit, the error impact will actually increase when the number of qubits increases. So when qubits number is 1,000 or 10,000 or 100,000, if you use an architecture that handles error correction, and that will be ideal. That is why we are working on this architecture. And since 2 years ago, working with Osaka University, sorry, I'm running out of my time. For example, surface code can be utilized on lattice. Gate set that is indicated here can be utilized. Okay, let's go C now, let's go S gate, let's go H. These rotations are at fixed angle, but if you can repeat, let's go H, let's go T, we'll be able to achieve a new architecture. Until the quantum beat gate operation for logical T are necessary. And as a result, currently we have increased qubit at increased number of operations. But if you can have phase rotation gates, if you replace logical T with phase rotation gates, we will be able to reduce the necessary resources. That is what we are proposing 2 years ago, since 2 years ago. NT gate replaced to phase rotation gate, quantum bit number can be 1/10, maybe 1/20th of gate operation numbers. And as a result, 64 qubit system can be applied to 10,000 qubits. That is something that we proposed 2 years ago. Sorry, I don't have much time left. That technology actually improved last year. Phase rotation gate is not protected by error, so phase rotation gate numbers are actually limited. Because of the error of this gate operation number has the upper limit. If we can reduce the error rate of phase rotation gates, there is small possibility. So phase rotation gate is something that we want to improve with these technologies. It's very difficult to explain this in 1 minute. So phase rotation gate error rate is now suppressed. And another thing that we did, even though we show the paper of star architecture, it's very difficult to understand. So what we did is, if you have quantum circuit, we developed a software that can convert it to star architecture automatically and use that tool for analysis. The result of the analysis is, this is Harvard model, first of all. Harvard model if the sizes increases, current FTCG is not going to calculate. 8 times 8 Hubbard model requires 5 years if you use HPC. So for this Hubbard model, we apply star architecture with 60,000 quantum bits. It takes only 10 hours instead of 5 years. With this number of qubits, quantum supremacy can be achieved. We believe this is the low score evidence of quantum supremacy. It requires 60 qubits, but if we can improve further, we'll be able to achieve less number of qubits to carry out this quantum calculation. Sorry, this is my last slide. As you can see, we are working and developed both hardware and software from both sides. We are trying to compete to quantum computing so that we'll be able to achieve a practical quantum computing. To do this, we alone will not do very little. So we need to work with all of you. We are actually promoting collaboration, and we would like to continue to partner up with all of you in the audience so that we'll be able to realize practical quantum computing. Thank you for listening.